Welcome back to The Explainer. Today, we are looking at an absolutely groundbreaking new paper out of Stanford University that completely redefines how AI actually thinks. We're always talking about throwing more compute at an AI to get a better answer, right? But simply throwing raw processing power at a problem doesn't always work out the way we want it to. Well, the Stanford team recognized this exact bottleneck and developed a brand new framework called Spiral. That stands for Sequential Parallel Aggregative Reinforcement Learning. And guys, it is an absolute masterclass in teaching an AI how to manage its own brain power. Let's get right into how it works.
Okay, let's dive into this, because it's pretty much the central paradox in AI right now. You would naturally assume that giving a language model more time and more compute to think through a really complex math problem would naturally lead to the correct answer. But researchers are noticing this very distinct, jagged edge in intelligence. When models are given extra sequential compute, meaning more time to think step by step, they frequently misallocate their budget. They end up writing out extensive, super repetitive details for basic routine operations, but then they just completely gloss over the complex, decisive logical leaps that are actually required to solve the problem. They basically hit a wall where extra compute just leads to redundant logic, not better solutions.
To understand why this happens, we have to look closely at how these models are trained in the first place. The core bottleneck is that during training, AI models are essentially treated like lone workers in a windowless room. They are optimized purely for straight-line sequential thinking. The model generates a single chain of thought and then gets a reward based on whether that one specific chain leads to the right answer. It is completely blind to parallel thinking. It has no idea how to explore a broad space of potential solutions all at the same time. Because they're never actually taught how to look at a problem from multiple angles during training, they just don't know how to do it when we test them in the real world. So the Stanford researchers propose that to finally break this bottleneck, an AI needs to master 3 distinct types of compute. Think of this like a team brainstorming session. First up is sequential compute. That's your solo draft, just taking a single thought straight from point A to point B. Second is parallel compute. This is the brainstorming phase, generating multiple independent ideas at the exact same time to explore different possibilities. And third is aggregative compute. Think of this as the manager's final pitch, taking all those messy ideas and synthesizing them into one polished final response. And right here is where the industry standard really falls short. Standard AI training focuses almost entirely on that very first step, sequential compute. So when practitioners actually want a model to brainstorm or synthesize at test time, they have to force it to do so using these really clunky hand-designed scaffolds and external tools. The model struggles because it was just never natively trained to juggle all 3 tasks. But the Spiral framework completely flips the script. Instead of bolting on these capabilities as an afterthought later, Spiral natively trains the language model to master all 3 primitives end-to-end, all inside one unified pipeline. Now, what's really fascinating here is how beautifully this entire end-to-end process maps out. Tracing from top to bottom, the initial input problem branches out as the model independently samples multiple parallel reasoning traces. Those are our brainstormers. Then, instead of just lazily picking the most popular one, the model takes all of those independent traces and synthesizes them into one final aggregation trace. The truly revolutionary part here is the credit assignment. Using only the single reward from that final aggregated response, the Spiral framework reaches all the way back and optimizes the entire pipeline. Now, you might be wondering, how on earth do you reward a bunch of different, completely independent ideas based on just one final answer? Well, the secret sauce of this paper is something they call set reinforcement learning. Instead of rewarding a single idea in a vacuum, SetRL assigns a shared learning reward to a collective set of sampled actions. It prioritizes the group's overall usefulness. It's literally exactly like grading a group project in school. You aren't grading each student on whether their individual contribution was the final perfect answer. You are grading the entire team on whether their combined efforts gave the manager what they needed to succeed. Let's contrast these 2 approaches to really see the difference. Standard reinforcement learning rewards a single trace in complete isolation. If a trace doesn't get the exact correct answer on its own, it gets penalized. But SetRL rewards a diverse team of traces that aggregate well together. This is a massive shift. SetRL explicitly encourages wild, out-of-the-box ideas. An individual trace might be completely totally wrong on its own, but it could contain the exact missing puzzle piece the aggregator needs to formulate the correct final answer. SetRL protects those diverse ideas because they ultimately contribute to the final victory. Let's step under the hood for a second to see how this actually works.
First, the model takes the problem and samples an array of independent search traces. Thanks to SetRL, the model knows it doesn't have to perfectly nail the final answer in every single one of those traces. Its job at this specific stage is to broadly explore the solution space. It's actively encouraged to generate a highly diverse set of potential paths and hypotheses without the pressure of having to be right immediately.
Next up, these independent traces are batched together into uniform groups. Think of this step like taking your massive pool of brainstormers and separating them into different conference rooms. Each room, or set, contains a completely unique combination of ideas. By grouping them this way, the model is perfectly setting the stage to see which combinations of ideas work best together when they are forced to collaborate and synthesize. And here we see that final synthesis step in action. For every single group, the model generates a final aggregation trace by conditioning on the initial problem and the specific set of brainstormed ideas in that room. Once these final outputs are evaluated, the system passes the learning signal all the way back. It uses standard RL to teach the aggregator how to synthesize better, and it simultaneously uses SetRL to teach the parallel traces how to brainstorm more useful combinations in the future. It is literally a co-evolutionary process happening continuously inside a single model. And we have the data to prove this diversity is really happening. Looking at the data for token-level entropy, which is basically a measure of randomness or diversity in the model's thinking over the course of training, we see a stark contrast. The standard GPRO training, our current baseline, steadily drops off. The model is collapsing into redundant, highly correlated attempts, effectively just giving up on exploring. But look at the trajectory for Spiral. It maintains high entropy throughout the entire process. Spiral fiercely resists collapsing into a single repetitive track. It is genuinely and continuously searching for diverse solutions. So what does this all mean for actual performance? Well, we can view this as a heavyweight match between the baseline GRPO and Spiral on complex math datasets. In standard Passet-K evaluations, where we just scale up the number of independent guesses, Spiral delivers up to 11 times the scaling efficiency compared to the baseline. Let that sink in for a second. 11 times. And looking at recursive self-aggregation, where the model repeatedly refines its own traces, Spiral pulls away with up to a 15% performance boost. By learning to orchestrate its own syncing, it fundamentally outperforms models that rely on external scaffolds. This specific finding is absolutely critical. A lot of standard AI pipelines use a simple majority voting rule. They generate, say, 10 answers and just blindly go with whichever answer showed up most often. It's basically like picking an answer out of a hat just based on popularity. But in reality, Spiral's model-based self-aggregation severely outperforms majority voting. Teaching the AI to actively read, synthesize, and correct its own diverse ideas is vastly superior to just trusting the most frequent and often highly repetitive output. So the really crucial point is captured right here when we look at token budgets. When you try to scale standard sequential compute, it eventually, inevitably, hits a wall. The context window fills up, the logic degrades, and performance just flatlines. But Spiral, especially when using recursive self-aggregation, efficiently turns massive token budgets into actual, continuous performance gains. It effectively translates raw compute power into a smarter, vastly more capable search process without ever hitting that same frustrating ceiling.
Let's quickly summarize the big takeaways here. First, AI absolutely must learn to brainstorm. Generating diverse parallel traces is essential for complex reasoning. Second, self-correction is a teachable behavior. We don't have to hard-code it anymore. Third, set reinforcement learning is the vital bridge that makes all of this possible. And finally, the entire future of AI scaling is about training models to effectively collaborate with themselves and orchestrate their own internal thinking.
Which leaves us with a truly fascinating question to end on today. If AI can now natively learn to brainstorm, orchestrate its own thoughts, and aggressively self-correct without human-designed guardrails, what limits are literally left to break? We are rapidly moving from models that just answer static questions to models that conduct autonomous, sprawling research in fractions of a second. The compute bottleneck is cracking wide open, and the era of self-orchestrating AI is just beginning. Thanks so much for joining me on this explainer. Keep learning, keep questioning, and I'll see you next time.